Okay, so just to remind you guys, on the Big Idea Notes page under 1B, I actually described the trends in the data that we looked at, the trends in the ionization energy data. These graphs are for first ionization energies. I talked about the main trends, and then I talked about the exceptions here in green and purple. I put the equations for multiple ionizations that we had talked about when we did ionization energy. What does it mean for the second ionization, the third ionization, and so on. I want to just do something very quickly. I want to go back to this data page that has all those ionizations on there, and I want to take an element kind of far down the periodic table. I'll say phosphorus here, and I want to make a graph of this data. Because I feel like it can be instructive to look at this data in a different way. You might be able to see some of those patterns with a little bit more clarity. So I'm going to graph phosphorus here. I'm going to graph its ionization number versus the amount of energy that it takes to remove that electron. This is phosphorus. Read that. Boom. This is the, I'll call it the nth ionization, right? So first ionization, second ionization, and so on. And this axis is ionization energy. Does anybody remember the units? Kilojoules per mole. All right, so what do we notice? Yeah, so we're pretty low in energy, low in energy, low in energy, and then we see this huge spike. What's that spike all about?
The closest orbital?
The two closest electrons.
Yeah, so the ones that take the most energy to remove are the ones that are closest to the nucleus. They have the largest charge that's pulling them in from the nucleus, the largest effective nuclear charge. So we talked about shells, right? So we would say that these two electrons are in that innermost shell, the closest shell to the nucleus. But if we look at the rest of the electrons, and if I change the scale a little bit, we can actually see a little bit of evidence that there's more than just the two shells in there. So we can't see the closest shell now because it's off the chart here, but we can see now, going up to 70,000 kilojoules per mole, we can see two groups of electrons here, right? So in phosphorus, there's actually three shells of electrons. There's that closest one that holds 2 electrons. The next closest to the nucleus, 1, 2, 3, 4, 5, 6, 7, 8 electrons in that one. And then the outermost electron for outermost shell for phosphorus holds 5. And we looked at a little bit of data comparing different elements, and we saw, well, not only are there shells in the atoms, there's also subdivisions of those shells, right? We talked about subshells. Can you see evidence of subshells in this data?
Not really.
Not really. Maybe I can make these a little bigger. Boom, beautiful. It's hard to say. You could maybe sort of trace this trend for the second shell and say, well, we would expect this ionization to be here. These two are a little bit higher, so maybe there's evidence of subshells going on here. You can sort of see it down with this third shell. Well, it's a little bit harder at this one, right? If I kind of cheat and extrapolate that out, you could say maybe it's a little bit lower than we would expect here, and so maybe there's some evidence of subshells in the third shell of phosphorus as well. But it's not perfectly clear. There's another bit of experimental evidence that we have that gives us indication that there are shells and there are subshells within the atom. And once we're done talking about this data, I'll actually come back and explain electron configurations as well. The data we're going to look at is called Photoelectron Spectroscopy. We call it PES for short. If we break down the name, what do we notice? Photo, light, electron, electron, tiny little negatively charged particles that are in the atom that can be removed from the atom, and spectroscopy.
I mean, it's visually.
Spec is like vision or like
Spec is probably something about vision. Spectrum is like the rainbow, all the colors of the light. And scopy.
It's like some sort of like collection or study of data. Like you call when you go to the doctor, there's like a bunch of different
Orthoscopics. Like when you stick a tube in somebody and look around at them, right? So basically what we're talking about is looking at different energies, looking at the different energies of electrons that come out of the atom when we shine light on them. If we shine light onto certain atoms and the light has sufficient energy, it can remove electrons from that material. It's called the photoelectric effect. Einstein got his Nobel Prize for explaining the photoelectric effect, not for relativity. Because what he said is, if we shine light onto a sample of matter, so here I've got this flashlight, I can change the wavelength here, I can change the intensity. If I shine light onto a sample of matter, under certain conditions, electrons come off. And his explanation for that, part of it was to change our understanding of what light is. Instead of viewing light as waves, like have been done for hundreds of years since Newton's time, he actually visualized light as little packets of energy. We call them photons. And he's saying that the photons from this light source are coming in there, interacting with the atoms in this sample right here. And if those little packets of energy have enough energy contained within them, they can excite electrons and remove them from the atom. They can produce these little blue guys here, which we call photoelectrons. Electrons that have been given enough energy that they move far enough away from the nucleus that they don't feel any attraction. They go flying off all on their own. What do you notice?
They slow down the farther away they get.
They slow down the farther away they get.
Or they change speed. Maybe they speed up. I think they speed up, yeah.
We'd have to maybe get
But
a ruler or something.
They're going different speeds.
There's definitely different speeds going on, right? How many different speeds?
3. Several. I don't know. A lot.
Well, it's hard to tell. With this simulation, what I can do is actually create an electric field in this region of space right here. So this little battery allows me to create a voltage within this region of space. And what happens when I do that is you can see that not all of the electrons are making it all the way across now. Right? By putting this electric field in this region of space, it must be, you can't see it from where you are, but there's little positive charges here. There's little negative charges right here. So when the negatively charged electrons get close to this negative plate, they get repelled. Okay? But notice, not all the electrons are getting repelled the same amount. There's some that are getting about this far before they lose all their momentum and they get pushed back. There's some that are making it almost all the way here, and there's some that are going all the way across. So I would say there are at least 3 different energies of electrons that are coming off of here. By energy, I mean kinetic energy, right? Which is related to how fast they're coming out. This is the basis for photoelectron spectroscopy. But what we have to understand is, why are there different speeds that the electrons are coming out of here? Well, I'm going to draw what's called an energy diagram. You guys may have seen these before. You guys seen something like this? Okay, I'll take that as a no. What I'm trying to represent here is the energy of those different shells that we looked at with the ionization energy data. So n equals 1 was the first shell, n equals 2 was the second shell, and so on. Now this is sort of reversed from the graph that I just made, because the graph is talking about how much energy it takes to remove an electron from that shell. In this case, the most tightly held electrons are actually on the bottom of this graph. And this dashed line up here represents, I like to call it n equals infinity. It's a shell that is so far up on this chain, the electrons would be so far from the nucleus that they don't actually feel any attraction to that nucleus. So this is the point where an electron can leave the atom.
If they don't feel any attraction to the nucleus, how are they part of the atom?
Once they cross this line, they're not.
So they're just out there?
Yep, they're just off flying into space. Okay. And PES, what we have to be doing is we have to get at least some electrons up to this level. If we don't get any electrons up to this level, we haven't provided light with enough energy to get them there. But let's say we have an electron down here. Hopefully when you guys looked at the Bohr model in your first chemistry class, you looked at those spectra of different elements through the diffraction gratings and you saw little lines, little colored lines. You guys remember doing that? Okay, I'm going to have to bring in some light sources and show you guys this. But if you take, for example, the light that's coming out of the fluorescent lights above us, if you look at it through a diffraction grating or through a prism, it's going to split that light up into colors. But what you'll see is, for most substances, if you excite their electrons, they move around within these different energy levels. So I can excite an electron from the first energy level to the second energy level, but it's not going to stay there. Electrons always try to get to the lowest energy level, the closest shell they can possibly be in. So if I excite an electron up to n equals 2, it'll jump back down, and in the process, it'll give off light. And so when we look at the spectra that different elements give off when we put them in a gas discharge tube, when we send electric current through them, you see these colors being given off, and each color corresponds to a different jump within the shells in that atom. And so you might see a blue color that represents some jump. You might see a purple color that represents a bigger jump. All right? We're not interested in just having these things jump around within the atom. We got to get them all the way out of the atom. So what we have to do is we have to send light. Where's my little purple guy here? We have to shine light onto this electron, And if that electron absorbs that light, we want to try to get it all the way up at least to n equals infinity. But usually, when we do that, usually we go up past n equals infinity. A lot of times, if we're trying to get electrons out of these really close levels, we shine X-rays. So we shine X-rays onto the sample, and the X-rays have so much energy they can kick those electrons all the way out of the atom. But when they do so, usually they have more than enough energy to kick it out of the atom. And so this difference in energy here, between how much it would take to just barely remove the electron and how much energy we've put in from the light, the extra energy there is going to be in the form of kinetic energy. So the reason that these electrons are flying across is because we've not just given them enough energy to get out of the atom, we've given them extra energy, and the extra energy comes into their kinetic energy. So I'm just going to put KE for kinetic energy. So the light that we've shined in, this has a certain amount of energy as well. And how do we calculate the energy of light? H looks like a V. It's actually the Greek letter nu, frequency. So for light, we can figure out how much energy light has by taking Planck's constant. What's Planck's constant? 6 point something. Luckily, you don't have to remember it. It's on your equation sheet. Get out your equation sheets. I told you guys under atomic structure, there's only two equations, and they're not Coulomb's law. So you got to have Coulomb's law sort of memorized. But it tells us that E equals H times what looks like a V. And on the right it says E is energy and V is frequency. It's actually nu, that's frequency. And then it tells us H right below that is, that's a small number, 10 to the negative 34th. Why is it so small? Because light's small. Yes, that is, when we calculate this energy, we're calculating the energy per photon, per one little packet of light energy. So this is the energy per photon. So we're going to have problems because remember when we were looking at ionization energy data, it was in kilojoules per mole. So we got to be a little bit careful in this unit, in this section with units, because if we're in energy per photon and we're trying to figure out how many kilojoules per mole it takes to ionize that electron, we're going to have unit troubles. All right, we'll do some problems. We'll talk about that. But basically, this whole line that I've drawn here, this whole black arrow, is really the energy that's being provided by this light source. So this energy is the energy of the photon. Right? But we said the photon had more than enough energy to get this electron out. The extra energy we call the kinetic energy. But the energy that it took just to get that electron out of the atom is really like the ionization energy, right? It's how much energy does it take to remove that electron from the atom. In PES, we have a different name for it. We call it the binding energy.
And is this equation all the energy or just the binding energy?
So the binding energy is just the amount to take that electron from whatever shell it's in and get it up to the point where it can leave the atom.
What does the equation solve for?
What equation? I haven't written any equation yet. I'll give you equation in a second.
And you did.
What equation?
E equals H.
Oh, this one. This is the energy of the photon. So we can use the H times nu to calculate the energy of the photon.
So is that like total energy or?
That would be the total energy that's being provided to the electron. So yeah, one thing we're going to do in this unit is we're going to say that in PES, the total energy that we put in is going to equal the total energy that the electron gains. So maybe I don't like this equation. We could say energy in equals energy out. Conservation of energy. Whatever energy we put into the system with this light, that's the energy we're going to get out in terms of the energy that went into the electron. So we could say the energy of the photon is going to equal the energy of the electron. We're just transferring energy from this photon to the electron. Well, we can, hold on, one more step here. The electron has energy in two forms, right? First, it gains energy in terms of being removed from the atom. So this electron energy is really the binding energy, plus, if there's any left over, plus the kinetic energy that that electron's going to have. So the electron's energy is a combination of the energy it takes to remove it, the binding energy, and the extra energy it has of motion, the kinetic energy. And the energy of the photon, we can calculate this with h nu. And then so we can say energy binding plus energy kinetic. Now this is pretty easy to calculate. If you know, like in this simulation, if you know what frequency the light is, or if you know what the wavelength is, notice the equation below the E equals h nu equation is C equals lambda times nu. That allows us to go back and forth between frequency and wavelength. So if we know the wavelength, we can use the bottom equation to calculate the frequency, and we can plug that frequency into the energy equation, and we can see how much energy the light had that we put in. All right, but we still have two unknowns. We're trying to figure out the energy holding that electron in the atom, right? The binding energy, which is very similar to the ionization energy. But how do we figure out the kinetic energy? Well, we figure out in a way that's similar to what I had to do in this simulation. Right? I had to apply some voltage that the electrons have to travel through, and by changing that voltage, I can get certain electrons to stop wherever I want them to. All right, in practice, photoelectron spectroscopy looks a little bit different. Here's sort of a schematic of what a very simple schematic of what photoelectron setup is going to look like. You have some X-rays that you're shining in. There's our h nu, right? That's usually the symbol we use for some kind of light that's providing energy to a system. We shine that light, we hit our sample, and then these photoelectrons come flying off. And the photoelectrons go into what's called an energy analyzer. And inside that energy analyzer is an electric field, just like we had in that simulation. There's a plate that has a positive charge, a plate that has a negative charge. And what happens in these analyzers remember, in the simulation, we had electrons moving at different speeds, and they were making it a different distance through that electric field, right? So when I apply electric field here, I'll maybe make it positive down here and negative down here. As the electrons come in, they're going to be repelled by that negative part and attracted to the positive part, right? Well, at the very end of this, there's going to be some sort of detector. And so if these electrons that are coming off of the sample, if they're not hitting the detector, I don't see any sort of signal. So then I turn the voltage up a little bit. And with more voltage, we're going to get a bigger curve. Okay, maybe they curve like that. Not quite there yet, right? I still don't get a signal. It's not until I get just the right voltage that the electrons will curve through this whole system and hit the detector, and I'll see a signal. So So PES data is really boring. It's like nothing, 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 boom! Spike. That's it. All right? Now, we saw in the other simulation there was multiple electrons, multiple speeds of electrons coming off of there, right? So if one type of electron is hitting, there's probably other electrons that are in this system that are just higher kinetic energy, so they're not curving enough, or maybe they were lower kinetic energy and they're curving too much. But as we change that field, all of those curvatures are going to change, and so whenever we get just the right voltage for a set of electrons to curve into the detector, we get a signal. And the signal that we're getting in this PES system is from the electrons that we're removing from the atoms. And because every electron starts out at a different energy level, if I put the same amount of energy into all my electrons, well, if we think about this line here representing the energy of the photon, if I now put it into this electron in n equals 2, is that the same size line? A little shorter, Jess?
I don't know.
Pretty close?
Yeah.
All right, we'll go with it. All right, so for this electron, I put the same amount of energy in. I'm just shining one type of light on there. But this electron takes less energy to remove. It's got a lower binding energy. So the binding energy here is smaller, but the energy put in was the same, so what's that going to mean? This one's going to be faster. This one's going to have more kinetic energy, right? So it's going to take a larger voltage to curve those electrons back into the detector. And so what we're really seeing in this data is an indication of how much of the energy we put in is going into taking the electrons out of the atom. We're really measuring the kinetic energy of the electrons, but using this equation, we can figure out if we know the kinetic energies and we know how much energy we put in, we can then calculate how much energy it took to remove the electron. That's called the binding energy. How are we doing? Making some sense? Okay. So let's look at a photoelectron spectrum. Actually, we're going to look at a very idealized photoelectron spectrum. This simulation I'm about to show you is also on the Big Idea notes. This is from, I think, Arizona State. And so we can go through for all the elements up to scandium, we can see what a sort of perfect PES spectrum would look like. You excited? You ready? You ready?
Overjoyed.
Cool. Boom. Hydrogen. Wow. Like I said, we start out, this is energy on this axis, we start out putting no energy into our energy analyzer, no electric field, we're not going to see any electrons. They're going to be flying through and just straight line, never going to hit that detector. But as we crank up the voltage, eventually we get some electrons curving into that detector. And the PES system already knows what the energy of its light source is, and it knows based on the electric field that it's applying what the kinetic energy of those electrons would have to be, and it just spits out a binding energy for us. Did you guys ever have to, in physics, like calculate the force on a charged particle moving through an electric field? No? Did you do anything with electric fields? You did the right-hand rule, I'm sure, right? And those kinds of things. There are equations that allow you to calculate, okay, if I know the mass of an electron, and I know how strong my electric field is, and I know how far it's moved in that field, I know what velocity it would have had to have for that particular curvature, right? And so kinetic energy is 1/2 mv squared. This thing can figure out, what kinetic energy those particles must have had.
So is none of the binding energy or the kinetic energy?
This is the binding energy. We don't care about the kinetic energy. We want to know how much energy it took to remove that electron. So this is the binding energy. PS data is always going to tell us the binding energy. All right? and we see it's 1.31. There's no units on this thing. That was not very smart of them. Okay, but let me go back to the ionization energy data from Wikipedia. Look at hydrogen.
So it's just joules per mole, not kilojoules per mole.
Close.
Did I go the wrong direction?
Wrong way.
I don't know how to go the other
Because
way.
if it takes 1,300 kilojoules, and the other thing said it only took 1.3, it's not measuring in kilojoules, it's measuring in megajoules. Millions of joules. Kilos 1,000,
Okay.
megas a million. Okay? So really this is 1,300,000 joules per mole, 1.3 megajoules per mole. And notice for hydrogen with only one electron, its ionization energy is going to exactly match the PES data. Right? Because there's only one electron in there, it shouldn't matter how we remove it, the measurement it takes to, how much energy it takes to remove the electrons should be the same, right? Okay, so we see an exact match for hydrogen. Alright, now let's look at helium. You excited?
They can have two.
One spike. Only one spike. It's a little bit taller than the spike was for hydrogen, and it has shifted farther down the graph to a higher energy. So what does that tell us if we only see one spike? We know helium has 2 electrons. But if we only see one spike, what does that mean?
So I'm going to the first one. The second one. Is it average then?
They're the same. Both electrons in helium have exactly the same energy. What's nice about this PES system as opposed to ionization energy, remember in ionization energy we had to remove one electron, then we had to remove another electron, and we had to keep going one electron at a time. And so as we kept removing electrons, it kept getting harder and harder to remove them. In PES, we can hit one electron without touching any of the others. So it gives us a little bit different picture of how the electrons are arranged. Because we only see one spike, and we know there's 2 electrons in helium, we say that those 2 electrons have exactly the same energy. All right. Why is it higher energy than it was for hydrogen? One more proton, right? The more protons, Coulomb's law says, the more force is holding those electrons in, the more energy it's going to take to remove them.
What do you mean when you say they have the electrons have the same amount of energy?
It takes the exact same amount of energy to remove both the electrons in helium.
When we looked at ionization energy, so that wasn't true. It took more to remove the second one than it did the first one.
Because of the way electrons are removed when we're measuring ionization energy, remember I said you have to put the gas into some sort of tube and you sort of turn up the voltage, you send electrons through that tube until electrons get knocked off of the atoms. But you sort of have to do it and you turn up the voltage till you get one electron removed and then you're left with helium plus. To remove the second electron in helium plus is actually harder than to remove the first one.
This one, because you're like blowing them all off at the
Because
same
you're removing one and then you're taking it, the next electron is being removed from a +1 ion.
But
It's
for
not
this,
being removed
but
from a
for this
neutral
it's
atom.
not. It's just removed all at the same time.
Yeah, so for this, there's 2 electrons down here in n = 1, and you could hit either electron independently of the other.
Okay.
Okay? So yeah, with ionization energy, you might think there's some difference between the first 2 electrons in any atom. But PES says they're exactly the same energy. That's going to be important when we do our electron configurations. When we move to, actually if I go back here, 2.37, let's take a look at helium. Notice the first ionization energy for helium exactly matched. The second doesn't, because we just said the second one we're removing an electron from an already ionized atom, so it takes more energy. But the first ionization energy is always going to be the same as what we get in PES. All right, if we go to lithium now we have 2 peaks.
So,
Abdal?
So every like shell represents one space.
So the difference in peak is giving us some indication that yes, there's shells of electrons at different distances from the nucleus, which is why they take different amounts of energy to remove. Okay, we can see here now we have something at 6.26, which is way higher than hydrogen or helium was, but now we see one way down here at 0.52. Well, the easier to remove one would be that second shell, and the harder to remove ones are from that first shell. So again, the first shell of electrons in lithium are actually harder to remove than the first shell electrons in hydrogen or helium, because lithium has 3 protons. The outer shell, though, in lithium, even though there's 3 protons, that outer shell is farther away than the first shell, so these are actually easier to remove. Okay? Now we go to beryllium. Now this thing's a little bit weird. Instead of like just condensing the axis, it splits it up into multiple lines. So that peak right here didn't disappear, but it got so large it's off the scale here. For beryllium, it takes 11.5 megajoules to remove the hardest to remove electrons in beryllium. It takes more energy than in lithium. I can actually compare these. I could put lithium over here, and I could put beryllium over here. And so we can see lithium's easiest to remove electron from the second shell is easier to remove. It takes less energy than the electrons in that same shell for beryllium, because beryllium has more protons. So if we have more protons and we have the same shell, it's going to be harder to remove. Okay, you guys are looking extremely excited, so let's keep going. Boron, baby! What do we notice in boron? 3 peaks, right? Remember, Bohr said the second shell of electron can hold, the second shell of electrons can hold 8 electrons, right?
Why does it say 1, 2, 2?
The height is actually telling us how strong the signal is. So the more electrons are hitting that detector at that energy, the bigger the peak is going to be. So if we go back and compare hydrogen and helium, we should see that the peak for hydrogen is half as tall as the peak for helium. Because when we get to this energy for hydrogen, we get a certain number of electrons hitting the detector. When we get to helium, we get twice as many hitting the detector. Hello.
Hi, my name is Maha.
You are new?
Yeah.
Are you in 7th period or 8th?
8th and
Okay. You got study hall today.
oh, okay.
You'll come tomorrow.
Okay.
But you'll see me next period.
Okay.
Unless you want to stay. We're doing a really exciting.
Okay, I'll stay.
All right. Yes. See? She's like, graphs. I love graphs. I'm staying. Okay. So, yes, the height of this peak gives us an indication of how many electrons came off at that particular energy. All right. So, if we go back to boron, we see 3 different peaks, even though Bohr told us there were only supposed to be 2 different types of electrons, right? One's in the first shell and one's in the second shell. So there's got to be subshells, right? This gives us very clear indication that not all electrons in the second energy level are alike. Some take slightly more energy to remove than the others, okay? And what's interesting here is if we keep going through this second row, here's carbon, here's nitrogen, there's oxygen, fluorine, and neon. Notice that other peak keeps growing. So we can fit more and more and more electrons into this subshell, and this peak stays at a height of 2, and it just keeps going up in energy, right? Because as we're going across, we're adding more protons, right? We actually did see something, remember we talked about nitrogen versus oxygen? Kind of interesting, right? Remember we said it's slightly easier to remove the electrons in oxygen, at least those outermost ones, than in nitrogen, because of that pairing up of the electrons in a given region of space. We'll come back to that when we do electron configurations. But after we get done with neon and we move to sodium, we don't see this peak grow any higher, we see a new peak. And that new peak is quite a bit different in energy, right? This is almost a factor of 10 times the energy to go from this peak to this peak, whereas these two, it's only about double, right? And then to go from this peak up to wherever that last one is, it's about, what, almost 20 times higher, right? So even just looking at this data, we can see that there's 3 shells of electrons. There's a shell that's very close to the nucleus, huge amount of energy to remove. There's another shell that's sort of medium energies. It's split up into 2 subshells. One subshell holding 2 electrons, so we got a peak height of 2. And another subshell holding 6 electrons, so we got a bigger peak for this one. And then now we've added a 3rd shell with a much, much lower amount of energy. And then we can go to magnesium. Okay, again, we see all these peaks shifting to higher in energies as we go across and add more protons. Now we go to aluminum and notice that 3rd shell is now split into 2 subshells. Silicon, phosphorus, sulfur, chlorine, argon, right? Now it's kind of convenient that it has it on 3 different axes because we've got 3 very different energies, right? This is from 1 to 10, 10 to 100, 100 to 500, right? So the 1st shell, 2nd shell, 3rd shell. Guess what's going to happen when we click on potassium? Another peak. So now we've filled the 3rd shell, and now we're adding a 4th shell, right? And we look at calcium. What's going to be the difference for calcium? Well, we've started to add this 4th shell. Do you think this 4th shell is filled when it only has 1 electron? No. So we're going to see for calcium, we're going to see this peak gets higher. And we're going to see all the peaks shift to higher energy because calcium has more protons. All right. Now, what's going to happen for scandium? Okay, we're going to get another subshell, right? And where's it going to appear? Something like right here? Yeah?
Yeah.
All right, let's do it. Oh, no!
That scared me.
What's it doing over here?
That's a great question.
The heck is this all about? Weird. Right? This is the thing. This right here is the thing that prevents most high school students from being able to do electron configurations. Because when we start to describe the way that the electrons are arranged, we give symbols and letters to these different shells and the different subshells. And the names of them actually come from this type of data. When we looked at the electrons that are coming off of there, when we looked at all the energies of them, the S and the P and the D, have you guys heard of those? Those come from spectroscopy. S was from, they call them simple peaks. P, they call them principal peaks. D, they call them diffuse peaks. F was, I think, fundamental. So those letters actually have words that are associated with them when people did spectroscopy and they didn't really know what they were looking at. They just tried to, look for relationships. But now we just abbreviate them with S and P and D and F. Okay, so when we look at this data, when we look at a subshell that holds at most 2 electrons, we call that an S subshell. So in the first energy level for scandium, we only have 1 subshell, and it can hold 2 electrons. So in the first energy level, we have what's called the 1s subshell. And the 1s subshell, as I just said, can hold a maximum of 2 electrons. That's the highest that peak ever gets in any of these spectrum. And so to show those 2 electrons, we usually put a superscript of 2. If it's filled, hydrogen's electron configuration would look like this, 1s1. There's 1 electron. It's in the first shell in the s subshell. Okay? When we go to our next shell, the second shell, we have 2 subshells, one which holds a maximum of 2. That's again an s subshell. So after the 1s comes the 2s. For lithium, it would only have 1 electron in it. So this would be the electron configuration for lithium. 1s2, it's got 2 electrons in that first subshell, first energy level. It's got 1 electron in the second energy level, the s subshell. But that 2s can hold a maximum of 2 electrons. So this would be beryllium here. After we fill the 2s, right, that was this peak, then we started to see this peak appear. Because it has a different shape, we call it a different subshell. That's the p subshell. Second shell, p subshell, and it can hold a maximum of 6. It doesn't have to hold 6. If it just holds 1, that would be, well, 2 electrons here, 2 electrons here, 1 electron here. That's 5 electrons, that's got to be boron. But we can actually fill that 2p subshell. It can hold a maximum of 6 electrons. So this would represent neon, right? 2, 4, 10 electrons, right? You could just add up the total number of electrons. That's going to be how many are in that neutral atom. So this would be neon. After we fill that 2p, we see another one of these peaks that has a maximum height of 2. That's an indication of an s subshell. It's in a different shell than these, so we call it the third shell, the s subshell. It can hold a maximum of 2. After that one, still in the third shell, but with a maximum height of 6, that next peak represents a p subshell. It can hold a maximum of 6. Who would have this electron configuration? Argon. Pirate's favorite element? Argon. Okay. So after we fill that 3p, Aisha, I don't think you'd like that joke. After we fill that 3p, now we can see with a much different energy here, we've got a new shell. We call it the 4th energy level. Actually, it was this one. Let me click on calcium. Right? This peak here got to a maximum height of 2, so it represents an s subshell that can hold 2 electrons, and now's where a lot of people have problems. What comes next? You would think, like, looking at the pattern, it'd be a 4p, right? But because when we do PES on scandium, we see this little peak that actually comes in between the 3p and the 4s. It actually must represent a subshell of energy in between those 2 energies. And it turns out this simulation only goes so far, but if you kept going, what you'd see is this peak would keep getting larger and larger, but it would actually get closer and closer in energy to these 2 other peaks. So if we went to something maybe like copper, excuse my broken boards here, copper, let me draw it in blue. Well, it still has a 1s subshell, right? But copper having many more protons, that subshell is going to appear at a higher energy. It's still going to have a 2s and a 2p, but again, those are going to appear at higher energy. It's still going to have a 3s and a 3p, what you're going to see though for copper is that these two peaks are going to start to separate a lot more. So this peak here representing the 4s, it's still going to be higher in energy than for scandium here because copper has more protons, right? But this little peak here is actually going to start to approach these peaks here. And so we called this the 3s and the 3p. This peak's going to start to sort of bunch up with those. So we're going to say it's still in the third energy level, or the third shell. We're going to group it up with those, but it has a different maximum height, and so it's a different subshell, and we call it the D subshell. So after the 4s, we actually start to fill the 3D subshell. And when we look at PES data, the maximum amount of electrons that can fit into that shell is 10. And actually, I chose a horrible example to draw here because I made a mistake on this. Copper is actually an exception. This is what we might expect the PES spectrum to look like. In reality, copper's PES spectrum, the 4s only has a height of 1, and the 3D has a height of 10.
Why?
Why? That is a fantastic question. With a very, very complicated answer. So complicated that I do not have a very good way of communicating it to you.
Do other elements do that, or just copper?
Copper and all the elements below it, silver and gold, tend to have this exception as well. There's also an exception under chromium, molybdenum, and tungsten that occurs for a similar reason. It has to do with whether the D subshell is completely filled versus having the 4s subshell completely filled. And so it's actually more energetically favored for copper to completely fill up this 3D and to leave one electron out of the 4s, which is actually sort of unexpected. Okay? You don't have to know any of these exceptions, so if that didn't make any sense, just rewind your memory like 30 seconds. Okay? All right. So, how the heck are we going to remember the order that all these darn things come into play? I remember it using the periodic table. In your notes right now, I'd like you to draw an outline of the periodic table. Don't look, don't cheat, just try to draw it from memory.
I'm doing a pen.
If you use a pen, it's okay. If you make a mistake, you can just draw it again. Not bad. Not bad. Some of you are not entirely sure what the periodic table looks like. You kind of have the general idea, but not quite. So, the way it looks is there's a bunch of elements over here. There's a bigger bunch of elements in the middle. And then there's some elements over here. And then, because if we were to draw the periodic table the way it actually looks, it'd be really wide and super skinny, we put some elements down at the bottom that really belong up here. So if I were to really draw what the periodic table looks like, it would look like this, that would have those two really skinny rows that on my periodic table we chopped them off and like put them way off to the side. Then it would have a big chunk in the middle, and then a little chunk over here. Maybe not drawn perfectly to scale, that might be better. Okay? That's what the periodic table looks like now. In 10 years, when Bollium is discovered, I should say created. Bollium will never be discovered. You won't find it out in nature. You have to create it in a lab. All right. Once Bollium is created, we're going to have to put a whole nother set of rows on the periodic table. We've completely filled our bottom row on the periodic table. Element 119, we're going to start a new row. And once we get to element 121, we're actually going to have another even skinnier little row down here. Then the two rows that are down under ours, then another set here, and then another set right here. So your kids, you're going to say, back in my day, we didn't have this G block. It's these right here, the G block. They're going to say, oh, you're so old. They didn't know anything when you went to school. So the kids talk. All right? The way I remember the way the periodic table is set up is by blocks. I say this is the S block. This is the P block. In the middle is the D block. And down at the bottom is the F block. Why do we call them blocks? Because they're block shaped. They're rectangular. It's not anything fancy. All right, now you got to be careful when you draw this that you line things up correctly, because the S block is technically a little taller than the P block. And sometimes, a lot of people are drawing a little step here. I actually put the element that normally shows up here, I put it over here. Because it's easier for me to remember how the electrons are arranged, okay? Then I have to put two rows here until I get to the D block, and I have to mirror those two rows over there in the P block. And then I have to squeeze 4 more rows into the entire thing. So the S block is 1, 2, 3, 4, 5, 6, 7 rows tall. The D block is 4. P block is 6. And the poor little F block is only 2. Now, what I have to do to remember how electrons fill up is to remember which shell these types of subshells first appear. So S subshells, what's the first shell of electrons that we see S subshells?
The first one.
The first one, right? So this first row of the S block is representing the 1s subshell. Below that represents the 2s subshell, then the 3s subshell, then the 4s, and we just fill them down. Right? When your kids go to school, they're going to have another row here. They're going to have the 8s. But you guys don't have it yet because nobody's created Bollium yet. All right. How about the P subshell? What energy level or shell do we first see P electrons appear? Second energy level. So this row represents the 2p subshell, the 3p subshell, and we just fill them in. So now hopefully we can see a pattern. S appeared in the first energy level, P appeared in the second energy level, D is going to appear in the third energy level. You got to be careful because we had 4s here, but this first energy level for D we actually saw in the third shell. So this first row of the D block is the 3D. So when we read these things, this is how you're going to remember that first comes the 4s, then comes the 3D. Right? You have to remember that the first row of the D block is the 3D. The one below that is the 4D, then the 5D, then the 6D. Okay, then pattern-wise, F probably starts, even though we didn't see it in any PES data.
8 and 9, or 6 and 7.
Well, 1s starts here, 2p starts here, 3d starts here, 4F. Snaps, right? Now, if we want to know the full electron configuration for any element, we start at the top, we work our way down, reading left to right, just like a book written in English. Okay? So, if we start, the first thing we hit is the 1s. So if I'm writing electron configuration, the first thing I should always write is 1s. Now another nice thing about using the periodic table is if you look at how wide the block is, it tells you the maximum number of electrons that can fit into that subshell. So how many elements are in that column on the left? 2. So 1s can hold 2. We go across, there's nothing there, so we go to the next row. The next thing we hit? 2s. How wide is the 2s? 2 elements, so it can hold a maximum of 2 electrons. Again, remember lithium, it doesn't need to hold 2 because lithium only has 3 electrons. So lithium be 1s2, 2s1. But if we have to fill it, it can hold a maximum of 2. All right, there's nothing in the D block yet, so we go across. The next thing we hit is 2p. And count how many elements the P block has in it. 6. 6 elements in the P block, so any P subshell can hold a maximum of 6 electrons. After the 2p, we're done with this row. We go to the 3s, which can hold 2. Nothing in the D yet. Next thing across is 3p, which can hold a maximum of 6. Now we're done with this row. We go to the next row. We hit 4s, which can hold 2. Now we jump into the 3d. And if we count that D block, 10 elements wide, any D subshell can hold a maximum of 10 electrons. After the 3d comes the 4p, which can hold 6. Now we're done with this row. Next row starts with